Thank you, Joanne. Welcome, everyone. Thanks for joining us for this lunch hour primer on wireless LAN interference. And we thought that this would be kind of appropriate since we're coming towards the end of the summer. Fall's just around the corner. NFL season has kicked off, and Labor Day is coming up. We thought having a little bit of a sporting flavor would help a little bit. When I was asked to kind of explore what we would talk about here with wireless LAN interference, I really started off looking at some of the exotic interferers that most of you are familiar with already: microwave ovens, cordless phones, video cameras, and things like that, Bluetooth and other frequency hoppers. And that was kind of the first thing that entered my mind. And then when I started getting into this a little deeper, had a little bit of time to think about it, I realized there are some very critical wireless LAN interferers that kind of have dropped underneath the radar that I thought we should start talking about here. Now, the way this is going, we could actually expand this lunch hour session into several more versions of this. But to get started, I thought that a good understanding of wireless LAN in general, and also kind of what is mostly on the minds of most of the people who attend my class and that I talk to daily on a professional basis, is interference in the 2.4 gigahertz spectrum. So that's what I'd like to start with you today and explore that a little bit. Now, those of you who are coming in through the WebEx conference, notice on the right side of your panel, there's a couple of different ways that you can contact us. Sorry about having to mute the microphones. There's just too many attendees to allow for open mic and still be able to get all this content presented in such a short amount of time. So if you would, please, we do want to hear from you. We want to hear your questions and try to get the answers as best we can while still holding this down to a short session. So if you would use either the chat function or the Q&A function, we'll reserve a little bit of time at the end of this presentation to try to answer those top questions. Those we don't get to, we'll do our best to answer those in email. Thanks for participating in that. Okay, so back to the presentation. And you should see on your screen our opening slide that says call foul on wireless LAN interference. So let me attempt to turn the screen. You should now see the slide changing to our webinar outline. And number one on the webinar outline shows an introduction to wireless LAN spectrum analysis. Obviously, this will be a truncated version of an intro to wireless LAN spectrum analysis because that's a pretty deep subject. But we'll just kind of give an overview here. And then we'll talk about visualizing and analyzing 2.4 gigahertz wireless LAN interference. As I said, there are tons and tons of more topics, and we can go much, much deeper in further episodes of this presentation. But for now, we'll just concentrate on 2.4 gigahertz wireless LAN interference, and that should be enough to keep us busy for the next few minutes. Turning the slide one more time. And now you should see the title slide for this section, which is Intro to Wireless LAN Spectrum Analysis. With that, we begin with a slide, has a few bullet points on the left. Hope you're all seeing this with no problems. On the right, we see an example of a transmitter and receiver, and we're showing actually two separate waveforms which are in space at the same time. So many of you already know most of the stuff. I won't belabor the point, but it's important to remember that what we're dealing with at layer one, at the physical layer, when we're talking about wireless communications, is simply raw, naturally occurring energy that we've managed to harness in different ways through what we call modulation techniques. And these techniques allow us to harness this free-flowing energy and use it to deliver bit patterns. Okay, the bit patterns have to be precise. We can't stand for any type of errors in the system or in the stream, or else the communications is flawed, or I guess you would say it has been corrupted and has to be discarded. So it's kind of a critical method of transferring information. And the wireless air interface is probably the most hostile method, or at least medium, that you could use to transfer high-speed data communication. So all of that we have going against us in the first place. It's important, though, to remember that this energy has no mind of its own. It follows very few rules except the rules of naturally occurring electromagnetic energy, you can think of this as controlled bolts of lightning. Imagine a lightning bolt as it sparks off on a summer night during a thunderstorm. And sometimes a lightning bolt streaks across the sky in a regular jagged line, and sometimes it zips back and forth in different ways. Sometimes it's very bright, sometimes it's dimmer, and all of those things are similar to how electromagnetic energy that we use in Wi-Fi communications also acts. Now, when we have multiple streams of these energy patterns in the air that are all being received at the same time by a separate receiving antenna, this energy tends to add together. It's cumulative. And that means that there's a great amount of interference, which causes corruption to those bit streams. And so in order to visualize what's going on out there, because as you know, electromagnetic energy, not like lightning bolts, is invisible to the naked eye. And we have to have some type of tool to help us see and visualize what's going on in the area. When we transmit energy, what we typically do in Wi-Fi, using either the 2.4 or the 5 gigahertz range, using 802.11g or 802.11e method, 802.11a methods, we energize a center frequency. And when we energize the center frequency using different types of modulation, it creates sidebands out to either side of that center frequency. Now, the rules and regulations specify that the sidebands must attenuate by a certain amount by the time they reach a certain distance out from the center frequency. So without getting in too much technical detail here, just know that because of these rules and regulations and the power drop-off requirements, we tend to limit or think of the channels in an OFDM-style Wi-Fi channel as being 20 megahertz wide. That is 10 megahertz above and 10 megahertz below the center frequencies. And so you can see on the screen here that when we transmit from an access point or a station adapter that has been configured to use channel 6, when we actually transmit, we're actually encompassing or occupying bandwidth pretty much down to about the center of channel 4 and up to the center of channel 8. So that's that 20 megahertz of spectrum that we use, and it comes from the spectral density mask that you see on the screen. Now, most of you know that in September 2009, 802.11n was released, and 802.11n gave us quite a few new capabilities. And when we use 802.11n using one of the new features which allows us to expand our 20 megahertz channels to double that size by using something called channel bonding, then if you were to look at the spectral density mask, you'll see that it's identical, except that now, instead of encompassing or occupying bandwidth 10 megahertz above and 10 megahertz below the center frequency, we now occupy bandwidth 20 megahertz above and 20 megahertz below. That may sound like it's not important, but what really that does for us is that when we enable 20/40 megahertz channels, which is the official name of 40 megahertz channel bonded channels in 802.11n, when we do that, we're not really assigning like channel 6 and channel 1 together or channel 6 and channel 11. Instead, what we're doing is we're relocating the center frequency so that it's got 20 megahertz above and 20 megahertz below. And I'll show you better what I mean about that here in just a second. Let's go to one more slide here now. Okay, so here this is a good way to look at it. So here in the 2.4 gigahertz frequency range, as you mostly know, we have, generally speaking, 3 non-overlapping 20 megahertz channels, normally referred to as channels 1, 6, and 11. Looks like there's a little typo there. That should say 11 on the top subtitle. And you can see those on this graphic. Now, this graphic comes from a channel simulator I put together a few years ago that I think I'd like to share with you. Let me try to share my desktop now and bring up the channel simulator. Okay. Okay, here's our channel simulator. Hopefully that's all showing through just fine. And what you just saw was an example of a 20 megahertz channel, and it was centered first on channel 6. So I just clicked channel 6 and I turned on a 20 megahertz channel centered on channel 6. Now, what you're seeing is the bandwidth that would be occupied when the device that's camped on this center frequency channel 6 is actually transmitting. When it's not transmitting, when it's just listening, it's of course just listening on 2.437. But when it goes into the act of transmitting, we get this modulated sidebands on either side of the center frequency that occupies the 20 megahertz of bandwidth. Now, you all know that channels 1, 6, and 11 are referred to as non-overlapping channels. So I've just reached over and turned on channel 1, and you can see that channel 1 centered at 2.412 indeed does not touch the edges of the occupied bandwidth of channel 6. The same applies to channel 11. Okay, so I turn on channel 11, and you can see that we've got 3 megahertz or more of guard band in between these channels. But what happens if you turn on a channel in the center? Then you do get overlap. And this is when the energy patterns, like lightning bolts in the sky, tends to combine together, blend together at the receiver, causing corruption of the bits, and that's why we have CRC errors, collisions, and retries. Okay, so let me just turn on one more. I'll turn one on channel 9, and you can see what would happen. Now, keep that in mind because I'm going to show you a live example of what that looks like in the real world here in just a few moments. Let's turn these back off. And I'd like to show you also 40 megahertz channels in 2.4 gigahertz. So because of Data 211N, allowing us to select channels that are bonded to give us, in effect, a 40 megahertz wide channel when they're in the act of transmitting, by the way, then that means that in the 2.4 gigahertz range, which is a fairly restricted bandwidth, we have a choice of either setting, and I'm using the kind of the industry norms here. Most manufacturers will give you the choice when you set up an access point in 2.4 gigahertz for 2040 megahertz channels. You have a choice of selecting either channel 6 and the lower end of the spectrum, or channel 6 and the upper end of the spectrum. That's usually designated as primary channel 6, secondary channel -1, meaning the lower end, or +1, meaning the upper end. So let's take a look at what that looks like. Now, just a quick caveat for those of you who are attending from outside the borders of the U.S. So these restrictions are federal communications restrictions only. Other regulatory bodies would have different restrictions. However, since channels 1, 6, and 11 are so popular worldwide, this does have an effect and importance on any attendees from no matter what nation you're in. So please bear with me, and let me show you FCC 40 megahertz channels in 2.4 gigahertz. And notice what happens. So if you see the blue spectral density mask, it encompasses 20 megahertz above the center frequency, 20 megahertz below the center frequency. The way you would have assigned this channel would be by going into the access point and selecting channel 6 -1. But what that does is it moves the center frequency to 2.427, if you see what I mean. Now, I've been asked in the past, well, what about those frequency ranges down below channel 1? Well, the ISM spectrum actually goes down to 2.400. So there's bandwidth down there available. It's just there's no channels below channel 1 that you can manually select, if that makes sense. Okay, so now let's turn that one off and see what it would look like if you selected channel 6 +1. Let's do this, and there you go. So when you select channel 6 +1 in 2.4 gigahertz, what you're really doing is saying we want 2.447 as our center frequency. Now when we transmit, we expect to modulate outwards above that center 20 megahertz and below that center 20 megahertz. So we're really encompassing frequency ranges from channel 4 all the way up through channel 12. I think you get an idea of what that would look like if you had two access points with 40 megahertz channels nearby to each other, both talking fairly consistently. It would look something like that. See how the blue and the green overlap each other? And that is the prime recipe for collisions, retries, and CRC errors. Okay, there's our channel simulator. And I'll close that off and go back to the presentation screen. Please bear with me. There we go. Sorry, folks, doesn't seem to be going back. There we go. Okay. Okay, so sorry about that. It didn't go back to the presentation. I can get there. If you can see my screen, I'll just run the presentation directly from my PC. And I think we're on this slide like so. Okay, so you should see the screen that I left momentarily. And now you should know what these channel overlap masks are and what they're showing you. And the reason I was setting that up is because we're about to go into an actual spectrum analyzer. And I'm going to try to duplicate these scenarios with real live energy. And, you know, that's kind of what you need to learn with a spectrum analyzer. You know, it's one thing to picture it in your mind and pay lip service to, oh, yeah, channels 1, 6, and 11 don't overlap, yeah. But what you really need to do is be able to visualize that. And when you see it on a spectrum analyzer, understand what it is you're seeing. And that takes a little bit of practice. So let's go now to one of my favorite PC-based spectrum analysis devices, and this is one that happens to be marketed by Air Magnet, and it's the new USB format. I find it very responsive, fast, and has many different built-in applications, views, charts, graphs, and things like that. So the ones that I typically use to set up are I've put them on this screen. I usually start off with a rolling spectrogram, which is like an inverse waterfall. It looks like water falling uphill, except that the water is raw energy, and it's color-coded and kind of nifty looking. Next, I find a spectrum density display to have some value, and we'll talk about that coming up, and also the real-time FFT. And we can explore that in more details in just a few minutes. Let's move the screen now and talk about visualizing 2.4 gigahertz wireless LAN interference. In order to do that, you need a device that is part software if it's running on a PC and part hardware. These devices can be relatively expensive, but that's because they are precision devices and they need to be very fast and have a very low thermal heat signature that they give off. So I believe that a spectrum analyzer of some type is one of the most critical tools. It's a foundational tool for any wireless LAN engineer. I think there's really two that any wireless LAN engineer needs. At layer 1, we need a spectrum analyzer to see the raw energy, and you'll see why in just a few minutes. And then at layer 2, we need a protocol analyzer to look at the actual frames that are constructed from the bit patterns being carried by those energy waveforms at layer 1. But that's a topic for another time. So let's concentrate on the layer 1 RF energy at this point and practice visualizing 2.4 gigahertz wireless LAN interference. So here we have Air Magnet Spectrum XT, and I've brought this up and I've set it up so that it is in a baseline format. That is, I wanted to set this up in such a way that I was not seeing a lot of interference. So, you know, in today's world, it's kind of hard to find a place that doesn't have Wi-Fi and Bluetooth and all kinds of other types of electromagnetic interferers in the area. So fortunately, I'm kind of lucky and blessed at our location here. I have a cage area, I call it, which is not really a cage. It's just an isolated area where I have very low amounts of interference. And you can tell by looking at the screen. At the spectrogram, you see this pretty much blue. Notice that that's a very low amount of energy. And you can see in the spectrum density and also in the real-time FFT that the amounts of energy that are being detected are very low. Now, you might not know what constitutes low, so let's put a couple numbers around there. Here's a couple good numbers to keep in mind. Okay, anything above negative 85 dBm is likely to be an interference source. You can also have interference below neg 85 dBm, but in many cases, our wireless LAN radios have the ability to selectively ignore and communicate over top of energy patterns that are lower than neg 85 dBm. So we'll use that neg 85 dBm as kind of what we would call the clear channel assessment threshold, or possibly the lower level the threshold for selectivity, as it's called. Another number that you should keep in mind is the amount of noise that can exist naturally in a 20 megahertz channel, and we kind of peg that around neg 101 dBm. So two numbers, neg 85 dBm, that's a signal, still fairly strong, but it's a signal that most of our radios can still communicate without being affected by collisions in most cases. And then that neg 101, that's kind of what I call down in the mud. That's the naturally occurring noise level. So anything below neg 100, neg 101, that's really kind of safe if you have energy down below that. Anything below neg 85 dBm may be okay to communicate again. So I kind of set a baseline here to give us something to go on. If you look at the little scale down below the Spectrum XT chart, you'll see that's really just that Spectrum or the channel simulator with no channels turned on. We'll just use that as a point of reference coming up here on these next few slides. Lots of things to look at on this, but with limited amount of time, I wish we could explore all the little bells and whistles. We can only cover a few during this short session, though. So moving on, we've got our baseline, and now I'm going to flip the screen over and turn on one access point, or show you the results of turning on one access point. And there we go. So now on this slide, you should be seeing kind of a red area glowing, and if you look closely at the top spectrogram, and the spectrogram, this is kind of interesting, the spectrogram is actually historical data, and the spectrogram shows us scan lines. These are samples taken 1 second intervals, and if you look down at the lowest pane where it says real-time FFT, then if we were looking at a live spectrum analysis capture, which hopefully we'll have time for me to show you this live as well. But if we were looking at the live version of this, you would see that the real-time FFT has these squiggly lines go across the entire band, and then it refreshes every second. The spectrogram on top is an exact copy, but historically. So all of these scan lines appear on the top spectrogram, but over a period of time. In this case, we see the last 2 minutes worth of data showing up. If you notice in the spectrogram, historically, from the top down to just a little over halfway, notice that the intensity of the red area, the access point that was communicating on channel 6, was really just in idle mode. This access point was just sitting there, sending normal management traffic like beacons and things like that, not doing too much. It's just going on 10 times per second, sending out beacons. And this is, think of it as that lightning bolt as it blasts out. So it goes out quietly, 10 times per second, but then notice about halfway down, so right at about the 50-second mark, it got real bright and intense. Well, what happened there, if you had been here to witness, you would have seen right at the 60-second mark, I associated an access point, so the access, or a client adapter to the access point. And at that point, the client adapter went through all of his steps to get connected with the access point. And then I received an IP address. And then right about at 50 seconds, I started a JPerf throughput test. And what you're seeing is live TCP data going back and forth between one access point and one client on channel 6. That's about what it looks like. Okay, so it looks pretty intense. And if you notice over on the left, I've left open the panel that shows the duty cycle, and you notice that the duty cycle is changing. Notice that currently where I captured it, it showed that on channel 9 we had a 29% duty cycle. Actually, notice that, well, that's a little bit outside of our scope. I was gonna make a comment there, but I think I need to bail on that. I'm going to come back and talk about duty cycle a little bit later on because that's not matching up the way I thought it would. Sorry about that. More coming up on duty cycle, though. Changing the slide now. And now, so if you remember in the channel simulator, when I had gone and set 3 non-overlapping channels, you can see I'm on the bottom, channel 1, channel 6, and channel 11. Well, here's what I've done here in the lab. I've set up 3 access points, and these access points are just idling. I did not connect clients, did not start a JPER for an FTP session, so this is just standard management traffic, possibly beacons, probe responses, things like that going out from APs. And notice that's typical for what you would expect to see on 3 APs relatively near to each other. At standard, these are all set for 20 dBm or 100 milliwatt output on 2.4 gigahertz. Okay, so that's about what you expect. So one of the things that is really advantageous to you when you're working with spectrum analysis and just learning a new tool, for instance, is to go through, set up different test scenarios like this, things that you know that are common, and learn what should you expect. Because when you want to find abnormalities in your network, first you have to know what is normal. You have to know, how do I compare what I'm seeing now with what I expect to see? And so it's good to get your tools. Whatever spectrum analysis devices you may choose to use is fine with me, but learn to use that tool. Learn to recognize normalities and abnormalities. So here's what we would expect to see with 3 APs idling on channels 1, 6, and 11. Now let's look at a little different scenario. So I think I showed you this one on the channel simulator as well. I brought up 5 access points. I've set up the access points on channel 1, 3, 6, 9, and 11. So now I've got 5 APs, and look what happens. So when we have, and there's no user traffic on this, it's just APs idling, doing management traffic only. If we were to bring up client devices, even one on each one of this, you would see this whole thing turn almost solid scarlet across from channels 1 up to channel 12 and a half or so. So you can see the effects. We've got an AP on channel 1. We've got an AP on channel 6. Channel 3 fills in the middle there. So there's great potential, since channel 3 is overlapping the bandwidth required by channel 1 and 6, it's going to cause a great deal of interference, or at least it has the potential. Now, I want to be careful. It doesn't always cause interference, and it doesn't always make your network degrade properly or improperly. And we're going to talk about that in the very last section of this, analyzing to see whether or not these are actually causing problems in your network. Sure looks bad, but does it really cause a problem? For that, we need to dig a little deeper. Okay, before we go there, though, let's take one more look, and let's say look at the 2.4 gigahertz band, ISM band, from the perspective of 2040 megahertz channels. So here I have set up a single access point, and it is using channel 6 and -1. So remember when we looked at the channel simulator, I sent out channel sim at, when we select 6 -1, that really means that we're sending the center frequency at 2.427 or channel 4. And then we, when we transmit, we encompass frequency space 20 megahertz below and 20 megahertz above that center. And here's what it looks like in your spectrum analyzer. I'm looking mostly at the spectrogram because that's the obvious one right now. Now this, in order to get this to fire off, this is an interesting thing about 40 megahertz channels. When you just set up an access point and you select 2040 megahertz channels, until you actually start using the bandwidth required to expand over in the center or to the second channel, it doesn't use it. So it stays within the normal 20 megahertz until you fire off something that takes advantage of that second channel. And so in order to make channel 1 through 4 fire off and show you the second channel, I actually had to connect a client and begin a JPER throughput test. And once I did that, then we saw that the 40 megahertz channel became busy, occupied, and that's what it looks like. Now let's take a look at the 6+1, or the upper end of 2.4 gigahertz with 40 megahertz channel. And here we go. So again, on the bottom, just as a kind of a reference scale, we've got our channel simulator version, and it shows us that when we select channel 6+1, we're really setting the center frequency at channel 8, 2.447. That's all done automatically for you. There's not much choice you have over that. When you select 40 megahertz channels, at least in FCC nations, you'll be getting either the 140 megahertz below or 140 megahertz above channel 4 or channel 8. Okay. So once again, in order to make it use that second channel, I had to connect a client and start a JPerf throughput performance test. Okay, and that's what it looks like, just to give you a good idea. Okay, now let's take a look at what happens if you turn on both. So remember when I turned that on the channel simulator, and here's what it looks like. So I've got two access points using 2040 megahertz channels, one on 6-1, one on 6+1, and two clients both doing JPerf tests, and we've pretty much eaten up that band. So good luck. At least it looks like we'd be causing degradation to anybody else who is on any of the other channels, 1, 6, or 11. And indeed, that usually is the case. Also, look what happens to the noise floor. And I didn't mention this on some of the others, but if we were to go back and notice from our baseline how quiet it is up here on channels 12, 13, and 14, they were pretty much blue. But when we fire off a 40 megahertz channel, either below or above channel 6, then what happens is the whole noise floor rises. Now, we're going to talk about noise floor, natural interference, and things in an upcoming edition of this lunch spectrum analysis session. Just not enough time to cover that this week, but that's an interesting phenomenon. And what happens when you raise the noise floor, what that does to your modulation rates, what it does to your throughput, things like that. It's all interesting, at least to me, and I hope to share that with you in the near future. But for now, we'll just concentrate on the primary channels here. Okay, so moving on one more time, let's go to our final section, which is now analyzing that 2.4 gigahertz wireless LAN interference. So I've shown you some interpretations of the wireless LAN interference. And, you know, before we go further, let me just do one thing. Let's see if I can bring that up live and give you an idea of what that looks like live. Forgive me for having to work directly from my desktop, but that seems to be working the best for us. I'm just going to remote into our remote Access Labs, and let me set that for a little better color and scaling. And let's see if I can get in there now. Okay, so now we've got a PC that is actually running Spectrum XT on the screen. And okay, so here we've got live now. The order is a little bit different from what you saw just a minute ago. So let me set the order so it looks like what we were working with. I can go up. We've got 3 panels displayed. I don't have to show 3 panels. I could change that to show just the top, middle, or bottom graph. And many times I do. Many times when I want to look at detail, I'll just close off all but one so that it's as big and crisp and highest resolution as possible. But for now, we'll just go in and configure. I'm going to drop down the real-time FFT, and I'm going to open up the spectrum graphs and look at all the different types of spectrum displays that we have. I'm going to go with a spectrogram here. I like that waterfall, and you can see how the waterfall is displaying now. Also at the bottom, just to make it match, I'll go for a real-time FFT. Okay, so now if you watch the real-time FFT, you'll see that this is it's actually taking many samples per second, many thousands of samples per second, averaging those together and displaying one squiggly line each second across that bottom display. And then the upper display, the spectrogram, each one of those lines is in effect, it's the color-coded version of the bottom real-time FFT. So that's why you get to see this historical painting coming up the screen. Okay, so it looks like I've got a couple of APs on over there. We won't have time to go in and set up any labs, but in the future, perhaps we will have time to do some of that stuff. I'm going to leave the spectrum density alone for now, and yeah, boy, lots of things to explore here, but mostly I just wanted to give you an idea of what was possible. Before I go back into that analysis portion, I do want to touch on one thing. I'm going to come back down to the bottom pane and drop open that drop-down box, and I showed you quickly the spectrum graphs that were possible. Now I want to show you another feature that I think is just very, very useful. In order to view actual layer 2 information within this single application, AirMagnet has given us the ability, if we have a second Wi-Fi card, I shouldn't say a second, a supported Wi-Fi card, because the Spectrum XT card is not capable of doing Wi-Fi, it's not capable of associating to an access point and doing traffic. It's simply a spectrum analysis device. If we have a supported Wi-Fi card, that is specifically one that you would use to be able to associate to an access point, connect to the internet, send email, that kind of thing. If you have, in addition to the Spectrum XT hardware card, you have a Wi-Fi card supported by AirMagnet drivers, then you get all of this layer 2 live real-time information and the ability to display MAC addresses, SSIDs, security, all these different types of things. Okay, so that's an added feature built right into this. And the advantage there to have that all integrated into one application is what I want to show you next. So I'm going to, I think I'll close that out for now. We'll let it run in the background if we want to go back over there. Let me come over to the PowerPoint. Okay, and analyzing. Okay, so we've looked at the raw spectrum graphs and charts, and we saw that we have what really looks bad. Lots of red colors and yellow colors and jumping out. The thing about it is we don't really know if that's bad. And the reason why is because remember that right now we're talking specifically about 802.11 wireless LAN interfering devices. These are all devices that are using the 802.11 protocol. In another upcoming session, I hope that we can do non-modulated interferers and non-wireless LAN types of interferers like Bluetooth and things like that. They have a whole different outlook. But since we've only been talking about access points and client adapters who are sharing the 802.11 fair access protocol, then these devices have a politeness factor built into them. All of them take turns using the air medium. So even though we're seeing raw activity in the air, how can we tell whether or not that activity is detrimental to the performance of our network? And that's the next section that we have to understand. So there is a layer 2 protocol that assures fair access to all 802.11 wireless LAN devices. And it's actually 2 steps. There's 2 methods that are used. The primary method is known as the virtual carrier sense, and that really is a timer that is set on all devices, warning them that the medium is in use for a certain period of time. Please stay off until we get our transmission and acknowledgement through. And all devices participate in that as the primary method of collision avoidance in an 802.11 system. There's also a backup method. The secondary method is known as the physical carrier sense. That's the one that we normally think of. That's where the devices actually measure the energy that exists on the air interface and to determine whether that's above a certain threshold. And just for general purposes, you can think of that neg 85 dBm as your listen before talk threshold, and that might be slightly variable depending on the different technologies that you may use, but that's a good number to work with generally speaking. Neg 85 dBm, physical carrier sense, listen before talk threshold. Okay, so we've got this fair access politeness protocol built into 802.11 that says please don't talk unless you go through a couple of steps and assure that nobody else is in the middle of something before you do. And that only works with 802.11 devices. Bluetooth doesn't follow those rules, microwave ovens don't follow those rules, and that's why those are discussions that I'd like to postpone for another time. Okay. So talking about the CSMA-CA distributed coordination function in 802.11, then we need to look a little more deeply to see whether or not these spectrum patterns are telling us whether our networks are degraded because of this energy. And we can do that using different types of charts and views in the screens. So the first thing you can look at, I think, is the Wi-Fi graph that we saw that's called channel occupancy. So by looking at channel occupancy, if you look at the spectrogram right now, I actually have 2 access points configured right now. On channel 11, I have a standard 802.11g 20 megahertz access point. On channel 6, I have a 802.11n 2040 megahertz channel configured on a 802.11n access point. However, there are no client devices associated or performing any type of activity on the access point on channel 6. So we don't see that second 40 megahertz channel firing off. So that can be a little misleading. We look at the spectrogram and say, okay, it looks like I've got a 20 megahertz AP on channel 6, 20 megahertz AP on channel 11. But if you look at the channel occupancy screen that's built into the Wi-Fi graphs and look at the very first listing, we've got a Motorola AP7131, and you can tell by the slightly darker yellow color starting at channel 4 and extending all the way up to channel 12. Well, we may only be using 20 megahertz channel right now to send out beacons and management traffic, but we are signaling that we will, if necessary, occupy an entire 2040 megahertz channel. And that's what it looks like in the channel occupancy range. So this is a great screen for just doing quick tests and quick studies to see where are these devices actually located. So we can't tell if it's causing harm at this time. So we need to look at some other views to get an idea whether or not this is causing problems on our network. So we can look at things like duty cycle, which, if you remember, I started talking about it earlier, but the heavy duty cycle was on a channel that wasn't really applicable to what we're talking about. I said we'd talk about it later. Well, it's later. And we're looking at duty cycle. Duty cycle is a very, very good test to see how busy the channel actually is. So now, just so you know, to be fair, this is a 2040 megahertz channel that's configured for channel 6 plus 1, and I've got one client doing JPerf performance testing on that client. So this isn't just an AP idling. We actually have some TCP traffic going back and forth from AP to client and back. And you can see that the red levels from channel 4 on up to, this is showing all the way up to channel 14, and those would be actual overspill, adjacent channel interference caused by the activity here. And look at these numbers. We've got 86, 87% and higher, and the lowest we've got, when I did this screen capture, was about 38% utilization or duty cycle. So the way to interpret that is this. You can go and configure what you consider to be the critical level, and that may vary depending on the type of application you're using. So if you're supporting a wireless network and your types of data applications for your users are simple data, such as web browsing, print jobs, that type of thing, you may be able to tolerate traffic as high as 75 to 80% duty cycles on those channels. However, if you're looking for high-speed data, and the reason you implemented 40 megahertz channels so you get super high-speed data, but you have other 20 megahertz access points that are within range that you would notice from your site survey, you may only be able to support duty cycles up to about 20%. And if you've got quality of service real-time applications like voice and video, it's going to be much less than that. So can't give you a hard number, but these general numbers can be a very general guide for you on what duty cycles would be useful and appropriate for your applications. Here we have another screen called Retries and CRC errors, and this is usually one of the first things I look for when I'm trying to determine if the network is suffering degradation due to some types of collisions. Collisions typically occur from two different places. They can be from congestion, that is too many APs, or too many client devices, or not enough APs and too many users. Possibly too many APs on the wrong channels, too many APs on channels 1, 3, 6, 11, and 9, that type of thing. All of those can be causes of retries and CRC errors, which are the result of collisions. The other major area is interference, just general interference. So those are the two places we look for: congestion, too many users, not enough APs, or interference, too many access points on the wrong channels, or too many access points on the same channels, too many clients trying to talk at the same time, that type of thing. And in addition to those types of screens, those are some of my favorites, some of the first things I look for. But just notice here, I wanted to give you some, since we're talking about wireless LAN analysis now, and in an upcoming episode of this, I'd like to talk more about the spectrum graphs that we didn't cover, but I just wanted to give you a quick heads up and show you some of what the views are on some of these other Wi-Fi graphs. I showed you Wi-Fi devices, channel occupancy. I think I showed channels by retry and CRC, but there's plenty of others in there. Here's some additional ones that I find very useful. Wi-Fi devices, very useful. AP signal strength. Channels by speed is a good one. Channels by media can be useful if you're trying to compare 802.11g and N and A and B and all of that together to see what channels are being affected by what different types of medium. Then we have channels by address. And when we say address, I'm not talking about the MAC address. It's the type of traffic, whether the address is a broadcast, multicast, or unicast address. And that's very important because multicast traffic and broadcast traffic go out at particular rates that are standardized. They're governed by the standard. Unicast traffic will usually go out at higher rates than the broadcast and multicast traffic. So taking a quick look at that kind of gives you an idea about the health of your network. Channel utilization, another good one. Now this one particularly shows utilization by speed, so everything from 1 megabit up to 54 megabits and higher, and in some cases 802.11n speeds. And then another screen that can be useful for a quick view, just top 10 APs. So show me the top 10 APs, show me by speed, show me by media type, show me by CRCs and collisions and that type of thing. Just quick views that can tell you quickly what's going on onto your network. And one of the most important ones, channel signal-to-noise ratio. Signal-to-noise ratio is a good way to determine what the health of each one of the channels is, because in an upcoming session I hope to talk about noise floor and how noise affects modulation rates and throughput speeds and things like that. This channel SNR panel can give you a very quick view and a good way to look at what's involved there. Okay, let me summarize, and then we'll get into some Q&A. So to summarize, spectrum analysis is a fundamental wireless LAN skill set. We will use it for planning. We'll use it for troubleshooting. We use it very, very often for security. It should be part of your site surveying skill set as well. And to use a PC-based spectrum analyzer that allows mobility and the opportunities to sample and analyze out in the field at the point where the events are occurring is critical. So to have a lab desktop spectrum analyzer is nice, but to be able to pick it up and go out to a site where a user is complaining about intermittent activity or even long-term activity, to get right there where the events are occurring, that is extremely valuable. So PC-based makes it very, very handy. And remember that in order to diagnose the different types of events and issues that occur in 802.11, remembering that it's got this fair access medium, in other words, we're going to let everybody talk at some point, we're just not going to guarantee how fast they're going to talk, then knowing that, you will want to learn what all these different visualizations are showing you so that you can determine what's going on in your network. And Air Magnet Spectrum XT has all these features built in, plus an excellent expert system that can quickly take you from square one to square 10 in just a few clicks and a few views. and just a few moments of capturing. It also has the ability to capture long-term, save to file, and do analysis offline. So I find all of those to be critical and all of those to be excellent, excellently, if that's even a word, I should say, well-implemented applications and features inside the Spectrum XT product. Okay, so with that, I want to thank you for spending your lunch hour. I hope you were all able to have a bite while I was talking, and thanks very much for attending. Thanks to Air Magnet for having me out here, and thank you, Joanne, for putting on such a nice platform. Now, I'd like to take a look at some of the questions that were over in the chat feature. Let me see if I can get to that now. Let's try this. And okay, I got my first screen back. Let me just take this back to the end. Wait, shortcut. Yeah, there we go. Okay, now I've got chat. Here's Q&A. Let's see. Oh, yeah, got a few. Let's see. Most of these ones so far. Let's see, Mike, you said, is it fair to say channel bonding is not going to work out if you only have a 2.4 gigahertz band available? Here's the thing, Mike. Yes, I agree that you, generally speaking, unless you are isolated, completely back from all others, and you only have 1 or 2 access points and a few client devices, channel bonding in 2.4 gigahertz, generally speaking, is kind of a diminishing returns. It really, except in those isolated incidents, it really is not too beneficial. You may get some slight additional speed, but the interference that you give to your neighbors can end up actually forcing them to raise their power or add more access points, and that comes back as more interference for you. It's kind of a vicious cycle. In my opinion, 2.4 gigahertz should not be used for 2040 megahertz channels under any circumstances except the ones where you have no neighbors and only 1 or 2 access points. Okay, so, and again, that's an opinion, but it's also the one shared by the 802.11 Standards Association. When they released 802.11n, the word was out that 2.4 gigahertz really shouldn't be used for 40 megahertz channels and channel bonding. So, and then again from Mike, so really you need the 5 gigahertz band to make this channel bonding practical. And yes, when you go to 5 gigahertz, you have so many opportunities. We have 23 non-overlapping channels in the 5 gigahertz band, and that allows us to bond up to about 11 channels together for 40 megahertz channels and still have a couple of 20s left over for voice or whatever you may want to use. So the ideal area for channel bonding is in the 5 gigahertz band. And to explain that fully, I'd really like, I hope Air Magnet will invite me back to do another one of these sessions and let us go in and explore the 5 gigahertz band now the way we have the 2.4. And if you need a multi-AP environment, yes, that's correct, Mike. And let's see. And Mike, why don't we see lower levels in the guard band between non-overlapping channels? It may be because of something I neglected to, I'm not sure I understood the question. If this isn't the correct answer, shoot me another message. We'll see that, and I'll try to answer it more fully. But I think what you're referring to is the 3 megahertz of guard band showing between like channel 1 and channel 6. And that is because of the way the channels were originally divided up into 5 megahertz channels. And we can't separate one of those 5 megahertz channels, so we have to go in full increments of 5, meaning that from center frequency out to the edges, we encompass 5 of those 5 megahertz channels. That gives us not 20 megahertz, but actually 25 megahertz, which leaves either 5 or 3 megahertz, depending on whether we're using 802.11b, which, by the way, only uses 22 megahertz wide channels, or OFDM, which uses the 20 that I've been talking about. So I didn't really go into the details of 802.11b, but that's something else we could talk about in kind of detail. Let's see. And John, what generates a higher duty cycle in the environment? Good question. The reason you get a higher duty cycle is more activity. So the longer devices are in the channel, in other words, if you just have a client connected to an access point and every once in a while you ping, let's say even if you did a continuous ping, pings are fairly slow, and so you will see some activity. You'll see the duty cycle rise incrementally. But if you were to go through and do a continuous FTP session, you would see the duty cycle rise even higher. And if you were to do a bidirectional JPerf TCP performance test, which really kind of bangs on that channel, you would see the duty cycle go even higher. Another way to see the duty cycle rise is if you have lots and lots of additional users come into the area and all are connected and all are doing just even pinging and print jobs and web browsing and things like that. So hope that answers the question. And gosh, you guys, not just guys, but we've got some interesting questions from both males and females, and I don't think I'm going to get to them all because I've kind of eaten up my hour, and I hate to keep you from your desk. So Bruce, Harold, Malwin, Mike, Brian, Lewis, Keith, Al, you've got some great questions here. I'm afraid I'm going to have to sign off at this point, though. Doesn't mean that I won't answer these. Let me try to address these offline and get those back to you in email. I know I'd love to share these with the whole group, but I'm sorry. I just have run out of time. Too much talk, not enough answers. So, again, thanks a lot, folks, and I sure hope to see you again. Have a good rest of the week, and check back later on. Bye.